Look closely at their shapes. One is straight, another is curved, a third is inclined, another made of rock. Nothing seems to connect them, and yet they face exactly the same pressure. The real question is, why do we build such different structures to hold back the same water? What you just saw is not architectural detail. These are essential choices dictated by the force of water, by the geology of the terrain, and by the risks a dam must face throughout its life. And if these shapes vary so much, it's because no dam lives in the same conditions. In our daily life, we mostly see the lake, the landscape, sometimes the turbine or the spillway. But behind all that, a dam fulfills crucial missions. Understanding why a dam has one shape rather than another means understanding an essential part of hydraulic engineering and civil engineering. It means understanding how we tame a colossal natural force and turn it into a resource. In this video, we're going to see together why these shapes exist, how a dam stands against millions of tons of water, how it manages floods, what each structure is for, and what risks it has to face. Before even drawing a plan, engineers must answer a simple question: how will the dam resist? Should it rely on its weight, on geometry, on curvature, or on a flexible structure made of natural materials? This logic is what creates the major families of dams. The first family includes gravity dams. These dams resist essentially thanks to their own weight. Their shape is thick, stable, deeply anchored into the ground. They are suited to wide valleys with solid terrain capable of supporting a large load. Their philosophy is simple: oppose a colossal mass to the force of water.
Here, it's really brute force. We don't rely on finesse but on a wall so heavy that the water simply cannot push it.
Then there are arch dams. Their role isn't to resist alone, but to transfer all the pressure to the rocky walls of the valley. Their marked curvature is essential. It allows forces to be distributed laterally, making these structures very efficient in narrow, rocky valleys. Their effectiveness comes less from their weight than from their geometry. Finally come embankment dams. Unlike concrete structures, they are built with natural materials such as compacted earth or rockfill. They are more flexible, more tolerant to ground movement, and adapt very well to wide valleys. This is actually the most widely used type of dam in the world because it allows the construction of very large structures at a reasonable cost while offering a high level of safety. And on some sites, no single form is enough on its own. So several approaches are combined. You can have a massive section, another an embankment, another slightly curved. These are called compound dams, adapted to complex terrains and multiple constraints. In summary, the choice of shape depends on three essential factors: geology, the width of the valley, and the hydraulic forces the dam will have to withstand. A narrow, rocky valley calls for curvature. A wide, stable valley calls for mass. A less homogeneous soil calls for an embankment. Each context imposes its solution. Now that we understand why dam shapes vary so much, it's time to enter the structure itself. What is inside a dam? And what are all these elements for? To understand how a dam actually works, we have to look at what it contains. The first element is the dam body. It is what holds the water, resists the pressure, and transmits forces to the ground. In a gravity dam, the thickness of the concrete absorbs the force. In an arch dam, geometry transfers the pressure to the rock abutments. In an embankment dam, resistance comes from the compacted layers of natural materials capable of absorbing ground deformation. But a dam is only solid if its foundations are solid. The abutments and the rock base must be carefully prepared. Sometimes grout is injected to fill cracks. Drains are installed to evacuate infiltrated water, and the rock is checked to make sure it can support the load. The stability of the dam largely depends on what happens under its base, out of sight.
If the foundation isn't impeccable, even the most impressive dam can lose its strength. It's like a wall set on sand, sooner or later it moves.
Next come the bottom outlets. These are conduits located at the base of the dam capable of releasing a large amount of water. They are used to lower the reservoir level, manage sediments, or secure the dam in emergencies. They are essential elements for keeping control even in extreme conditions. Higher up are the intake structures. These are the passages that supply turbines, irrigation networks, or drinking water treatment plants. Their position depends on water quality and the required flow. With gates and penstocks, the flow can be adjusted precisely. Another critical element is the spillway. This is what evacuates floods. When a storm or snowmelt suddenly raises the reservoir level, the spillway allows water to escape without exceeding the dam's capacity. It can be free flow, gated, a weir, or even a labyrinth shape to increase capacity. The safety of a dam often depends on the efficiency of its spillway. Inside the dam, there are also galleries. They allow personnel to move inside the structure, inspect it, monitor cracks, check drains, and sometimes access instruments. These galleries are the technical heart of the dam and provide direct visibility into its condition. Finally, a modern dam is equipped with complete instrumentation. Piezometers measure water pressure in the ground. Inclinometers monitor movements. Pendulums detect deformations. Sensors record water level variations. Everything is monitored continuously to detect the slightest sign of weakness. Now that the structure is established, the internal components are in place, and monitoring is ensured, one central question remains. How does a dam handle the force of water on a daily basis? When we talk about dams, everything starts with an invisible but immense force: water pressure. The deeper you go, the higher the pressure. At the base of the dam, the force can reach tens of tons per square meter. The entire design of the structure depends on this reality. A gravity dam uses its weight to resist it. An arch dam uses geometry to transfer this pressure to the rock walls. An embankment dam distributes it gradually through its compacted layers. Holding back water is not a matter of simple thickness, it's a matter of balance. The dam must absorb or transmit forces, anchor itself in the ground, and work with the foundation. The way it reacts depends directly on its shape, its composition, and the quality of the terrain. A dam is a complete system in which each element carries part of the load.
It's like a giant balance. Change the shape or the ground, and the balance changes completely. That's why a dam must be custom designed.
Hydraulic functioning is not limited to retaining water. The level must also be managed. The reservoir is not always full. Depending on the seasons, rainfall, snowmelt, or downstream uses, the level varies. Engineers always keep a margin to anticipate floods. With gates, intakes, and the spillway, they can adjust the flow and maintain precise control to avoid overload. When a flood arrives, the spillway becomes the key element. Its role is to evacuate excess water before the dam is exceeded. Too little evacuation and the water rises dangerously. Too much evacuation and downstream areas are hit by a strong wave. The spillway allows controlled flow even in extreme situations. It is one of the most sensitive parts of the dam because uncontrolled overtopping can quickly erode the structure. The water leaving the dam can reach considerable speed. Without energy dissipation devices, it would cause massive erosion in the riverbed. This is why dams are often equipped with stilling basins or devices that force the water to lose energy before rejoining the river downstream. This prevents the river from deepening or destroying its banks. Slower but equally important, another phenomenon occurs inside the reservoir: sedimentation. Particles carried by the river settle at the bottom. Over the years, the useful volume of the reservoir decreases. The bottom outlets can help evacuate some of the sediments, but siltation remains a major challenge for dam longevity. Finally, what a dam does downstream is just as important as what it does upstream. By modifying the natural flow of the river, it influences ecosystems, agricultural uses, drinking water supply, and navigation. Maintaining an environmental flow is essential to preserve aquatic life and river balance. Now that we understand how a dam manages water and controls its flow, it's time to see what happens to all this stored water. What is it actually used for? When a dam holds millions of cubic meters of water, it's not just to form a lake. This reserve plays a crucial role in the daily life of millions of people. It secures access to water, produces energy, protects valleys, and supports ecosystems. The stored water becomes a strategic resource managed carefully throughout the year. The first use is drinking water. From the reservoir, water is taken at different depths, where quality is most stable. Suitable intakes avoid surface layers, often warmer or more loaded with organic matter. Once captured, the water goes to treatment plants before supplying cities and villages. During dry periods, the presence of a dam ensures continuous supply even when the natural river weakens. The second use is irrigation. Thanks to controlled flow regulation, water can be distributed to agricultural areas. Dams ensure irrigation during the dry season, increasing crop productivity and securing harvests. In many regions, modern agriculture wouldn't exist without these reservoirs.
For farmers, a dam is not a landscape element, it's insurance, a way of knowing water will be there when needed.
The third use is hydropower. The water head stored creates pressure that drives turbines. These turbines power generators that produce electricity. Hydroelectric dams can adapt their production to demand by increasing or decreasing flow. It's renewable, stable, dispatchable energy, though dependent on available storage. A dam also protects against floods. When a flood arrives, the reservoir can absorb part of the water before releasing it gradually. This retention capacity reduces downstream risks. Dams are therefore key elements of flood management strategies. During dry periods, a dam takes on another role, supporting low flows. It releases just enough water to maintain aquatic life, drinking water supply, or some agricultural uses. This is called environmental flow. Without regulation, rivers could become almost dry in summer, with major consequences for the environment and populations. Reservoirs also serve other purposes: fishing, navigation, swimming, recreation, tourism. Many reservoirs become attractive areas where local economic activities develop. But all these uses are only possible if the structure remains safe and monitored. So how is a dam controlled daily, and how is its stability evaluated?
Dams are structures that seem simple when observed from a distance: a wall, a lake, gates. But behind this apparent simplicity lies complex engineering where every detail matters. The shape of the dam, its foundation, its internal galleries, its spillways, and its monitoring systems are never left to chance. They result from a meticulous balance between geology, hydraulics, safety, and human needs. But they are also infrastructures that must be designed, monitored, and managed with great rigor to ensure safety and durability. If you want to go further on this topic, tell me in the comments which dam you would like us to analyze in a dedicated video.
And now, grab a glass of water and stay hydrated. If you're into this topic, don't forget to subscribe, hit the bell, and come with us to explore the world of water.